Stop for a second. Think about the shortest unit of time that truly matters to you. Is it, I don't know, a fraction of a second? Is it a human lifespan? Maybe 8 or 9 decades.
Or even on a grand scale, you might think 4.5 billion years, the age of our planet, is a huge number.
Right. But whatever scale you choose, it's insignificant. It's nothing compared to the universe's true history and its future.
Exactly. We're scaled to biological time, maybe geological time if we really stretch our minds.
Hmm.
But when we talk cosmology, we're talking about deep time.
Deep time.
The universe is about 13.787 billion years old. That number it's functionally impossible for our brains to process intuitively,
Yeah.
and that's just the past.
And that profound gulf, that gap between our existence and cosmic existence is exactly what we're diving into today. Our whole mission is to take this incredible stack of sources you've brought, articles on everything from stellar thermodynamics to particle physics, and pull out two enormous contrasting timelines.
We are first going to compress the entire past, all 13.8 billion years of it, into this single familiar frame. We're going to use the cosmic calendar.
Which I love. It really illustrates just how fleeting our moment has been.
And then we're going to flip the timeline completely. We'll stretch the clock forward into this terrifying, mind-bending future. We're charting events that measure time not in billions, but in trillions, quintillions, and exponents that define the final cold endgame of the universe.
This deep dive is really our shortcut to understanding the biggest story ever told. I mean, the story of everything, from the fiery birth of the cosmos to the final silent whisper of matter decay.
And what's fascinating here, what makes this possible, is the mathematical precision of these theories. They're rooted in thermodynamics, in quantum mechanics, and they allow us to explore events that are trillions of years beyond the lifespan of our own sun.
We're charting chronologies that stretch into numbers that are literally difficult to write down.
So we're going to treat time itself as our source material today. We're navigating these vast scales to understand what's important, what's inevitable, and, why should we even care about the ultimate fate of everything, given our infinitesimal place within it all.
Okay, let's unpack this. We have to start with our very, very fleeting moment in the grand scheme of things. Let's start with the cosmic calendar. The cosmic calendar, which Carl Sagan famously popularized, is just brilliant because it takes something completely incomprehensible.
That 13.787 billion years of cosmic history.
Right, and it makes it visceral. It scales that entire duration down into one single calendar year starting January 1st at midnight.
The time compression needed to do this it's truly staggering. And I think we have to establish those conversion rates just so you can feel how tangible this history is about to become.
Okay, so what are the numbers?
To fit 13.8 billion years into 365 days, a single cosmic day has to represent 37.8 million years.
37.8 million years.
In one day.
In one day. And a cosmic hour clocks in at 1.58 million years. And here's the one that always gets me. The most humbling number of all. A single cosmic second, just one tick of the clock, represents 438 human years.
So when we finally get to human history, everything we think of as civilization, as progress, all of recorded history, it's all going to be measured in tiny, tiny fractions of a second.
So January 1st, midnight, what happens?
That's the Big Bang itself, January 1st, 0.000. But what's really remarkable is how fast the foundational elements of the universe appear, the moment the universe cools enough for photons to travel freely.
That's the event that creates the cosmic microwave background, right? The universe's first light.
That's the one. That happens at January 1st, 12.14 a.m.
Wait, 14 cosmic minutes. Just 14 minutes after the beginning.
14 minutes. Before that, the universe was this opaque, white-hot fog of plasma, and then suddenly it was transparent. The light we detect today is still the oldest, coldest remnant of that original heat, and it continues rapidly. By 12:30 a.m. on that same cosmic day, January 1st, the first stable atoms have formed, mostly hydrogen and helium. Then we enter this long period, the cosmic dark ages.
A long stretch before any structure emerges.
Exactly. It takes nearly a full cosmic month for the first known galaxies to form. They pop up around January 26, and they finally begin to illuminate that dark void.
So that feels like a slow beginning in a relative sense. Galaxies are forming through February, but our own home, the Milky Way, it only begins in March.
Our own island universe, the Milky Way galaxy, doesn't even start to form until March 1st. And it takes all the way until May 13th for its spiral disk structure, the one we recognize, to fully organize itself.
So the universe is already about a third of the way through its existence on this
A
calendar.
third of the way through.
by the time our immediate neighborhood even starts to look like itself, and Earth and the Sun are still nowhere in sight. When does our stellar system finally get its start?
For that, we have to leap all the way across the summer months. We land in September. The formation of the solar system, the sun igniting, that's September 9th.
And the Earth and Moon.
They form almost right away, just 5 cosmic days later on September 14th.
So the entire history of Earth, all the geology, all the life, everything has to be crammed into the final 4 months of this calendar.
It's an incredible compression, and the pace of biological evolution immediately puts pressure on that timeline. By September 21st, we see the emergence of the first life.
That fast. Less than a week after the planet formed.
Based on the oldest rocks we have that contain evidence of life, yes. Simple prokaryotes. Life arises fast, but complex life
Takes forever.
That is the critical observation here. Early life spends the next month basically evolving photosynthesis. That arrives around September 30th. But the great oxygenation event,
That's when photosynthesis basically dumped so much free oxygen into the atmosphere, it caused a mass extinction for all the anaerobic life.
a total ecological catastrophe at the time, but it set the stage for us, and that doesn't happen until October 29th.
Okay, so now we're rushing toward the end of the year. The first complex cells, the eukaryotes, they arrive November 9th. The entire age of visible life, the Phanerozoic eon, is all packed into December.
The first true multicellular life doesn't appear until December 5th. Simple animals follow quickly after that, around December 7th. So if you think about the entire history of life on Earth, complex visible organisms have only been around for the last 27 days of this cosmic year.
And land colonization. Plants and insects moving out of the oceans.
That's December 21st, the winter solstice. And then comes the age that captures everyone's imagination.
The dinosaurs.
The dinosaurs arrive on December 25th, Christmas Day on the cosmic calendar, and they dominate the world for 5 full cosmic days.
5 days. That's a testament to their evolutionary success.
It's an incredible run, and their reign ends abruptly, disastrously on December 30th at 6:24 a.m. with the massive impact that caused the Cretaceous-Paleogene extinction.
5 days of dominance, wiped out by a cosmic fluke.
And that clears the stage for the Cenozoic era, the age of mammals, which happens entirely on the penultimate day, December 30th. Even the most primitive primates don't show up until that morning.
Which brings us to the final critical day, December 31st. And this is where the scale shift becomes truly, truly staggering. Our ancestors only arrive in the final hours.
The human lineage, the genus Homo, appears remarkably late. The first stone tools, the emergence of Homo in general, that happens on December 31st at 10:24 p.m.
10:24 at night. That's just 96 minutes before midnight. Our entire evolutionary journey from early hominids to us is less than an hour and a half on this calendar.
It is. And modern Homo sapiens don't appear until December 31st, 11:52 p.m. 8 minutes to midnight.
So everything you learn about in history class, Babylon, Rome, the Industrial Revolution, all of it happens in the last minute of the last day of the year.
The Neolithic Revolution, the invention of agriculture, that moment we stopped just hunting and gathering and started building permanent settlements. That doesn't occur until 11:59 and 32 seconds p.m.
Just 28 seconds before the year ends.
And let's really break down that final minute, because remember, every cosmic second is 438 human years.
Okay, lay it on me.
The unification of Egypt, proto-writing, the early Bronze Age, that all happens at 11:59 and 47 seconds.
So 13 seconds to midnight.
And if you look at the major intellectual shifts, classical antiquity, the Iron Age, the philosophies of Buddha and Confucius, the rise of the Roman Republic, the birth of geometry, that entire magnificent era starts at 11:59.53 p.m.
Wait, so the Roman Empire and the entire philosophical tradition we trace back to Greece lasted for just 6 cosmic seconds.
That's it. It's staggering. The invention of the numeral 0, the Islamic Golden Age, the medieval period, the Renaissance, that takes us to 11:59.55 p.m.
Which leaves modern history. Everything since the 16th century, the scientific evolution, the Enlightenment, all the major wars, computers, spaceflight.
All the cultural and technological acceleration that we feel defines our species.
Is the final single cosmic second. 0.59.59.
Carl Sagan captured this perfectly. He said that if the cosmic calendar were scaled to the size of a football field, then all of human history would occupy an area the size of his hand.
It's an infinitesimal sliver of time. It really makes you feel incredibly lucky to be alive during this brief, beautiful period. The clock striking midnight isn't just the present moment, it's the end of the past. So now we have to flip the script entirely and stare into the void ahead. A journey into truly unimaginable durations where the clock just keeps on running.
The cosmic calendar showed us the 13.8 billion years of the past. But that past was defined by the stelliferous era, the time when stars shine, when matter is organized. Now we move into the future. And even the near-term fate of Earth involves timescales that stretch far beyond our comprehension. We're charting the decline and eventual end of our home system.
And the change starts almost immediately, geologically speaking, long before the sun itself becomes a monster. We're talking about shifts that will erase any human legacy completely.
Within the next 1,000 to 10,000 years, the Greenland ice sheet is projected to melt completely. And that's pretty much locked in, regardless of what we do now due to climate inertia. It's going to alter global sea levels irreversibly.
And even our best efforts to communicate across that time, things like the waste isolation pilot plant markers.
The ones designed to last 10,000 years to warn people away from nuclear waste.
Right. They'll have barely started their job.
But 10,000 years is nothing to geology. In 50,000 years, Niagara Falls will be gone. It will have eroded the last 32 kilometers to Lake Erie and just cease to exist.
And our greatest monuments, the Great Pyramid.
Without constant maintenance, it'll be unrecognizable in a million years. Even something as dramatic as Meteor Crater in Arizona will be completely gone, just smoothed over by erosion.
So the soft human stuff is erased, but the planet just keeps churning. What about threats from space?
The celestial threats really ramp up within the next million years. Red supergiants like Betelgeuse or Antares, they're likely to go supernova. They would briefly outshine the moon and be visible in Earth's daylight sky.
And we're also due for more direct hits. The models suggest a high probability of Earth being struck by a kilometer-sized asteroid within the next 500,000 years.
And arguably more worrying is the close encounter with the star Gliese 710. In about 1.3 million years, it's going to pass very close to our solar system.
I won't hit us, though.
No, but its gravitational tug is strong enough to seriously perturb the Oort cloud, that massive reservoir of comets out there. It's going to dramatically increase the risk of cometary impacts in the inner solar system for millions of years after it passes.
And geologically, the Earth itself will be unrecognizable.
Absolutely. In 10 million years, the East African Rift Valley floods. A new ocean basin forms as the Red Sea pours in. Africa will literally be split in two.
And in 50 million years, Africa collides with Eurasia.
And that collision closes the Mediterranean basin completely, creating a new, massive mountain range on the scale of the Himalayas. Continents grinding into one another.
So new oceans, new mountains, cosmic bombardment. But the true existential threat for the solar system starts when the sun itself begins to change. When does our environment become truly hostile?
The critical phase really kicks in around the 1 billion year mark. See, the sun is slowly converting hydrogen to helium in its core. This makes the core contract and heat up, which in turn increases the rate of fusion. So its luminosity, its brightness, just steadily rises.
The first warning sign is subtle, though. A 1% increase in output over 110 million years.
But the ripple effects on Earth are catastrophic. It initiates this positive feedback loop with the carbon cycle. The increasing solar heat speeds up the weathering of surface rocks.
And rock weathering pulls CO2 out of the atmosphere.
Exactly. It locks it into the ground as carbonates, which seems counterintuitive, right? You'd think more heat, more life. But it's a fatal mechanism because plants need CO2 to live.
So the planet starts to suffocate.
By about 500 to 600 million years from now, the CO2 levels fall so low that C3 photosynthesis, which is used by about 99% of plants today, becomes metabolically impossible. The ecosystem collapses long before the heat itself becomes truly unbearable for animals.
And during that same window, something else final happens. I saw in the sources that tidal acceleration will have moved the moon too far away from Earth.
That's right. It ends total solar eclipses forever. No more of those perfect alignments.
Okay, so planets start dying off. What's next?
By 800 to 900 million years, CO2 levels fall even further, ending C4 photosynthesis, the hardier kind used by glasses. Without plants recycling oxygen, the free oxygen and the ozone layer in the atmosphere just vanish.
And that's the end for multicellular life.
All of it. All animals. Some extremophiles might cling to life for another 100 million years, but complex life is finished.
And then the planet itself dies, geologically. You mentioned the death of plate tectonics.
Yes, around 1.1 billion years. By this time, the sun's luminosity is up by 10%. The Earth enters what's called a moist greenhouse state. Surface temperatures reach 47 Celsius or 116 Fahrenheit. But the real problem is the runaway evaporation of the oceans.
Why does that stop plate tectonics?
The crust can only slide because the mantle beneath it is lubricated by trace amounts of water that get recycled when ocean plates subduct. When the oceans evaporate, that water lubricant is gone. The mantle stiffens and the plates just seize up. Geological recycling ends forever.
So by 1.3 billion years, we have a geologically dead planet, hostile to everything, but maybe the absolute toughest single-celled organisms.
All eukaryotic life is long gone, wiped out by CO2 starvation. Only prokaryotes remain, maybe deep underground. By 2.8 billion years, surface temperatures hit 147 Celsius even at the poles. All remaining life is extinct.
It's a slow, agonizing end. Billions of years of just increasing heat, but the final destruction of the planet itself is much more sudden.
Much more. The Sun leaves the main sequence in 5.4 billion years. It begins its expansion into a red giant. Its outer layers just swell up dramatically.
And even before it swallows us, the heat is incredible.
Well before. Between 3.5 and 4.5 billion years, the Sun's luminosity is up to 40% higher. Surface temperatures reach over 1130 degrees Celsius. Hot enough to melt rock.
When it finally balloons, how far out does it reach?
It reaches a maximum radius about 256 times its current size. The models are pretty clear on this. Around 7.6 billion years from now, the Sun will expand past the orbits of Mercury, Venus, and almost certainly Earth and the Moon.
They just fall into the expanding star.
They're very likely destroyed, vaporized by the incredible heat and drag. That's the complete annihilation of the inner solar system.
That's the final curtain for our star.
That's it. By 8 billion years, the Sun sheds over 45% of its mass through intense solar winds. It contracts rapidly, and it settles into its final form, a carbon-oxygen white dwarf. A dense, dim ember. And temperatures on any surviving outer planets will plummet, ushering in the next era, an era of darkness and decay.
We've just jumped from the final cosmic second of history to 8 billion years into the future. But that's just the end of our solar system. Now we have to expand our horizon again, stepping into what's called the degenerate era. This spans from 10 to the 14 to 10 to the 40 years. The scale is, well, it's becoming genuinely intimidating.
It is, and before the true cold really sets in, the gravitational choreography of our local neighborhood has to complete. In less than 5 billion years, so slightly before our Sun even becomes a red giant, the Andromeda Galaxy will have fully merged with the Milky Way.
Forming a colossal elliptical galaxy, right?
Yeah.
They've nicknamed it Milkomeda.
That's the one. And it's important to stress this is a gentle collision. The space between stars is so vast that individual star systems rarely, if ever, actually collide. Any white dwarf sun and its remaining planets would likely survive the merger just fine.
But that's just the start of the mergers.
Just the start. Over the next 100 billion to 1 trillion years, all of the roughly 47 galaxies in our local group triangulum, the Magellanic Clouds, all of them, will coalesce into that one single giant Milkomeda galaxy.
And here's where dark energy, the force driving the universe's accelerated expansion, fundamentally isolates us. By 100 to 150 billion years, all galaxies beyond our local Milkomeda cluster will have disappeared. They'll be beyond the cosmic light horizon.
This is a profound cosmological shift. Because of that rapid expansion, the light from those distant galaxies will never, ever reach us again. Any future observer in Milkomeda will be completely isolated. They'll see nothing but their own local group.
All the evidence we used to discover the Big Bang, the Hubble flow, the standard candles, it'll all be gone.
Gone. Cosmology, as we practice it today, becomes impossible for them.
So we're stuck on this dark island. How long until the lights go out completely inside Milkomeda?
The end of the Stelliferous era, the age of shining stars, that's set at about 100 trillion years. That's 10 to the 14. That's the great boundary marker of the deep future. By then, even the most frugal, longest-lived stars will have finally run out of fuel.
The red dwarfs. The tiny, dim stars that burn their hydrogen so incredibly slowly, they were the last bastion of light.
Precisely. Stars like Proxima Centauri, they'll burn out in about 4 trillion years. The absolute least massive stars, they might survive up to 10 or 12 trillion years. After that, they too contract into white dwarfs, joining the huge population of stellar remnants.
And the universe just turns dark. What's left are stellar corpses. White dwarfs, neutron stars, black holes. Is there any light at all?
Very occasionally, yes. Some marginal starlight remains. You might see a rare Type Ia supernova from 2 white dwarfs colliding. Or maybe a new, very short-lived red dwarf created by the chance collision of 2 brown dwarfs, but they're incredibly sparse and brief. The sources say that on average, only about 100 stars will still be shining in the entire vast expanse of the Milkomeda galaxy.
100 stars in a galaxy that used to have billions.
Hmm.
So now we enter this truly cold, slow phase dominated by gravity and time. We're moving to quadrillions of years.
And this phase is governed by something called dynamical relaxation. In a dense system like a galaxy, stars and stellar remnants are constantly interacting gravitationally. During these close encounters, they exchange energy.
So some objects get flung out and others spiral inward. It's a slow, violent sorting process.
It is. And on the timescale of 1 quadrillion years, that's 10 to the 15 stellar close encounters, will have detached all remaining planets from their dead star systems. They become free-floating, rogue objects just drifting in the void.
And the galaxy itself starts to dissolve.
Over the next vast period, 10 to 100 quintillion years, that dynamical relaxation process accelerates in Milkomeda's core. These interactions become so common that they eject 90 to 99% of all the brown dwarfs and stellar remnants from the galaxy,
They're just shot out into intergalactic space.
leaving Milkomeda nearly empty. The vast majority of matter becomes exiled, just drifting forever.
And the tiny percentage that remains inside.
They fall inward. They fall toward the central supermassive black hole. Even if an object escapes being ejected, it's still subject to gravitational radiation decay. Any binary system, two white dwarfs orbiting, or even a planet orbiting its star, slowly radiates energy as gravitational waves.
And that loss of energy makes their orbits shrink over time.
Yes, our sources confirm that if the Earth had somehow survived being engulfed by the red giant sun, its orbit around the black dwarf sun would decay, and it would finally collide in about 10 to the 20 years.
100 quintillion years.
Yeah.
It's a staggering length of time, but it's still relatively fast compared to what comes next.
It is. The final act of this era happens around 10 to the 30 years. By then, the last remaining non-ejected objects, the handful of stellar remnants still inside Milkomeda's gravity well, they finally fall into the central supermassive black hole.
Fueling it, making it slightly larger.
Before the universe goes completely dark, save for the massive black holes themselves, the universe is now vast, dark, cold, and almost entirely empty, dominated only by the immense silence of these gravitational prisons left behind.
We've crossed into a realm where timescales are no longer defined by gravity or star lifetimes, but by the fundamental instability of matter itself. When we talk about the ultimate fate of the universe, the end of all things, we're really dealing with a catastrophic race between two incredibly complex and very different scenarios.
This is a high-stakes competition. It's defined by the limits of particle physics and entropy. So scenario A is the slow, grinding process of heat death that's driven by proton decay and Hawking radiation, and it leads to the absolute maximum state of entropy.
And scenario B.
Scenario B is the instant, violent phase transition known as false vacuum decay.
Okay, let's start with scenario A with heat death. This begins with the disintegration of the very building blocks of matter, protons, which are stable according to the standard model of physics. But for the universe to reach maximum entropy, that stability has to fail, eventually.
That's right. Grand unified theories, or GUTs, which were developed to try and unify the fundamental forces, almost all of them predict that the proton must eventually decay into lighter particles, like antileptons.
And the estimates for how long that takes are all over the place.
I mean, we're talking about an incredible disparity. The shortest, most optimistic estimate for the decay of all nucleons in the universe is around 2 times 10 to the 36 years.
Which is already an immensely large number.
Far longer than the current age of the universe. But the more complex theories suggest a much, much longer lifespan. The slowest estimate our sources provide goes all the way up to 10 to the 200 years.
But in either case, the result is the same. All baryonic matter, everything we know, the substance, eventually dissolves into a soup of high-energy photons, neutrinos, and leptons.
Exactly. And if protons do decay, then by about 3 times 10 to the 43 years, the only remaining large structures are the black holes themselves. They are impervious to proton decay. This marks the beginning of the black hole era.
But even these ultimate survivors are not permanent. And this brings us to Hawking radiation, one of the most brilliant and, frankly, counterintuitive predictions in all of physics.
It is. It centers on this concept of quantum fluctuations near the event horizon. Quantum mechanics tells us the vacuum of space isn't really empty. It's constantly boiling with these virtual particle-antiparticle pairs that pop into existence and then immediately annihilate.
But near black holes' event horizon, that dynamic changes.
Right. The intense gravity is so strong that sometimes, just as a pair is created, one particle falls into the black hole and it carries negative energy with it. The other one escapes as a real observable particle.
So the net effect of that negative energy particle falling in is that it slightly reduces the mass of the black hole. The black hole is literally evaporating.
It's shrinking bit by bit through this quantum process.
Hmm.
And the smaller the black hole, the faster it evaporates because its curvature is more intense.
So the timescale for this depends entirely on the mass.
On the cube of the mass, actually. A black hole of one solar mass, the remnant of a single star, takes a staggering 1.16 times 10 to the 67 years to decay.
And the supermassive black holes, like the one at the center of Milkomeda, are orders of magnitude larger.
Milkomeda's black hole is estimated to take roughly 10 to the 91 years to vanish. That's a 1 with 91 zeros. If you wrote 1 0 every single second, it would take you over 3 years just to write that number down.
And it gets even bigger.
It does. The absolute largest structures, these ultramassive black holes that might form from collapsing galaxy superclusters, they could take anywhere from 10 to the 106 to 2.1 times 10 to the 109 years to decay. Once those final giants fade, the black hole era is definitely over.
And beyond that, beyond 10 to the 109 years, we enter the dark era. Nothing left but a diffuse cold soup of subatomic particles, just gradually approaching its final state of maximum entropy. The ultimate upper estimate for this complete final state is calculated at 10 to the 120 years. The scale it's almost a form of intellectual violence. Okay, so that slow thermodynamic end is profound, but it's a kind of gentle, patient finality. Scenario B, the false vacuum decay, or the big slurp, that's the opposite. It's instantaneous, it's violent, and it happens without any warning.
This concept relies on the subtle dynamics of the quantum fields that permeate the universe, especially the Higgs field. A true vacuum is the stable, global minimum energy state of a field. Our universe, however, might be stuck in a higher energy state, a false vacuum, fundamentally metastable.
Like a ball resting in a little dip on a big hill, just waiting for a nudge to roll all the way down into the deeper valley.
That's a perfect analogy. If that deeper, more stable valley, the true vacuum state, exists, then the universe is living on borrowed time. The decay happens through quantum tunneling. It's called bubble nucleation. A tiny region of space, purely by chance, tunnels through the energy barrier into the true vacuum state.
And once that bubble forms, it doesn't just sit there.
No. That bubble instantly expands outward, accelerating at nearly the speed of light. And when it hits us, the consequences are catastrophic because the fundamental constants of nature are different inside the bubble.
The sources cite this chilling conclusion from the physicists Coleman and DeLucia about this.
They realized that if you include gravity in the model, the geometry of spacetime inside that bubble changes radically. It would cause immediate, rapid gravitational collapse. They were explicit. The altered physics would cause life and chemistry as we know it to cease instantly.
Instantly, as in microseconds.
Yes. Far faster than any chemical reaction or conscious thought could possibly be completed. It is the ultimate cosmic reset button.
So we have to ask, is there any evidence we're in a false vacuum? Why is this taken so seriously?
The focus is on the electroweak interaction, which is linked to the Higgs field. And the stability of our vacuum depends on very precise measurements of two particles, the mass of the Higgs boson and the mass of the top quark.
And why those two specifically?
The interplay between their masses determines the shape of that quantum energy hill. And current measurements suggest that the minimum of the Higgs potential may not be the true minimum, that our universe is pseudo-stable. It's stable enough that the tunneling barrier is huge, but it still has a finite probability of decay.
So what's the timeline for that decay based on these measurements?
The calculation for the vacuum's lifetime, based on the standard model, is greater than 10 to the 65 years. And crucially, that's much, much sooner than the 10 to the 109 years needed for Hawking radiation to finish its work. If this is our fate, the big slurp wins the race.
This raises a question that's caused some public concern. Could we accidentally trigger this with something like the Large Hadron Collider?
The fear is that a high-energy collision could act as a nucleation seed, the push that makes the ball roll down the hill. But the scientific consensus on this is very reassuring.
Why is that?
Because the energies produced by naturally occurring cosmic rays that hit Earth's atmosphere all the time already exceed the energies of the LHC by millions of times. If a human-made accelerator posed a threat, the universe would have ended long before the sun even formed, just from natural collisions.
So the ultimate fate is this catastrophic race between a cold death over 10 to the 109 years and an instant light-speed quantum dissolution that could happen in 10 to the 65 years. Before we leave this era, we have to talk about the one philosophical idea that tried to beat entropy. Freeman Dyson's theory of eternal intelligence. He looked at the second law of thermodynamics and tried to find a mathematical loophole that would allow consciousness to survive infinitely.
It was an incredibly elegant piece of theoretical work. Dyson proposed that in an open, expanding, cooling universe, intelligent life could adapt its metabolism to experience infinite subjective time using only a finite amount of energy.
Infinite thought with finite energy. How does the math even allow for that?
The loophole is in something called Landauer's principle. It establishes the minimum thermodynamic energy cost required to erase one bit of information, which is a necessary part of any computation or thought. And that energy cost, EBIT, is directly proportional to the absolute temperature, T, of the environment.
So as the universe cools down, T approaches zero.
And the energy cost per thought also approaches zero. Dyson's insight was that life could perform computations with progressively less energy, but to do so, they would have to stretch their thoughts out over infinitely longer periods of time, waiting for the universe to cool just a little bit more.
So they would go into these progressively longer periods of hibernation. Wake up, have one slow thought, hibernate for 1,000,000 years, wake up again.
Exactly. By stretching out the intervals, the accumulated subjective experience, the total number of thoughts, could theoretically be infinite, even with a finite energy budget. It was a beautiful defiance of cosmic doom.
But it was invalidated by real-world observation. What crushed this hope?
The observation of the accelerated expansion of the universe, dark energy. Dyson's theory relied on the assumption that the temperature T would approach zero indefinitely.
And dark energy stops that from happening.
It does. In an accelerating universe like ours, a cosmological event horizon forms around any observer, and this horizon produces thermal radiation, known as the Gibbons-Hawking temperature.
So the universe doesn't just keep getting colder, it hits a minimum non-zero temperature floor.
Precisely. Because of this horizon radiation, the ambient temperature T never reaches zero. It has a permanent non-zero minimum, which means there is a permanent non-zero minimum energy cost for every single thought. Since the total energy is finite, any intelligent life is restricted to a finite number of thoughts.
That is a crushing finality. The laws of physics allow black holes to live for 10 to the 109 years, but the acceleration of the universe itself defeats the hope of eternal consciousness. We've talked about events that are 10 to the 109 years away, a number that's already beyond comprehension. But now we have to discuss the truly bizarre scenarios that only play out on timescales, that dwarf even the evaporation of the largest black holes. These are the realms of deep quantum tunneling and, well, statistical freakouts.
We are entering the realm of exponential towers. Time so vast that the difference between 1,000,000,000 years and 10 to the 109 years becomes basically negligible. These events assume that scenario A, the gradual heat death, happens, and that proton decay is either exceptionally slow or just doesn't occur at all.
So if protons are stable, matter is still not permanent because of quantum effects acting on rigid objects.
That's right. On the order of 10 to the 65 years, the same time frame as the fastest false vacuum decay estimate quantum tunneling takes over, even in bulk matter. Rigid objects like rogue planets and dead stars will just rearrange their atoms.
So matter starts to behave like a liquid, even at absolute zero.
Essentially, yes. The atoms of a rock would, given enough time, eventually tunnel into a slightly lower energy configuration, resulting in a slightly smoother, more perfect sphere.
And the matter itself is undergoing a slow transformation if the protons don't decay.
Yes. In the deepest future, if protons are absolutely stable, all baryonic matter will eventually decay or fuse into the single most stable isotope in the universe, iron-56. This process leads to the theoretical formation of iron stars.
And even these ultra-stable objects have a lifespan that just beggars belief.
Their lifespan is utterly staggering, 10 to the 1,500 years. But even an iron star is not truly permanent. It's still subject to the laws of quantum tunneling.
How does a whole star collapse via quantum tunneling?
It has to spontaneously tunnel through the immense quantum barrier that holds it in its current state. The entire star has to wait until the random motion of all its particles spontaneously and perfectly aligns to punch through that barrier, initiating collapse into a neutron star or a black hole.
And the time frame for this is where the numbers become just genuinely mind-breaking.
This is where we see the exponential towers. The collapse timescale is estimated at 10 to the 26 years at the low end, or 10 to the 10 to the 76 years at the high end.
Those numbers are so vast, their digits wouldn't change whether you measured them in nanoseconds or star lifespans.
The sheer scale is beyond any intuitive comprehension. It's the ultimate expression of extremely low probability physics.
And beyond the decay of structured matter, we enter the time of ultimate statistical oddities. Given infinite time, anything that can happen will happen.
Which leads us to the idea of Boltzmann brains. In an expanding, mostly empty universe, a self-aware consciousness could spontaneously appear via a localized quantum fluctuation, a massive temporary decrease in entropy.
A brain, floating in the void, fully formed, just long enough to be aware of itself before dissolving back into nothing.
The estimated time for this thermodynamic miracle to occur is 10 to the 50 years. That's a 1 followed by 10 quintillion zeros.
If even that is possible, then the recreation of the entire universe must also be possible, given enough time.
Exactly. This is the final, most mind-boggling estimation. Quantum tunneling in isolated patches of vacuum could generate new inflationary events, new Big Bangs. The estimate for this statistical freakout to occur is 10 to the 56 years.
That's not just a big number. That is the time required for quantum mechanics to undo everything that came before it, purely by chance.
And our sources go one step further. They state that this is also the theoretical time required for a quantum-tunneled Big Bang to produce a new universe identical to our own, particle for particle. The final statement of physics is that if time is infinite, even the lowest probability event imaginable, the spontaneous recreation of our entire reality, is guaranteed to occur.
We started this deep dive with the Big Bang, where the universe's first light appeared just 14 cosmic minutes after creation. We raced through the entire history of life on Earth in just over 4 calendar months, compressing all of recorded human civilization into the final single cosmic second of the year.
We then stretched the tape measure back out to examine a future so vast that the destruction of Earth by the Sun in 7.6 billion years is a mere geological hiccup. We learned that due to accelerated expansion, any future cosmic observer will be utterly isolated in a cold, lonely galaxy, unable to see the original Big Bang.
And we charted the universe's ultimate fate, which is a catastrophic race between the gradual decay toward heat death, measured over 10 to the 109 years, and the instant total collapse triggered by false vacuum decay, which could happen much sooner, 10 to the 65 years from now, with a collapse measured in microseconds.
We also found that the theoretical resistance to entropy, like Dyson's eternal intelligence, is mathematically defeated by the physical reality of the Gibbons-Hawking temperature, meaning even the most evolved consciousness is bound to a finite number of thoughts.
We looked at the final stages of matter, where iron stars collapse over 10 to the 76 years, and the time required for the ultimate statistical fluke, a new, identical universe spontaneously tunneling into existence, is measured at 10 to the 10 to the 10 to the 56 years. We are so privileged to exist during this minuscule time slice, this brief, beautiful, stelliferous era, where there is still light in chemistry to support complex, curious life.
So what does this all mean for us? If everything from the fleeting brilliance of a supernova to the ultramassive black hole at the center of a supercluster will eventually dissolve into a near-infinite void, what does that say about the importance of our own existence?
The sources seem to suggest that maybe meaning isn't found in permanence, because nothing is permanent. It's found in the fleeting brilliance of the complexity itself. The ability to exist, to use chemistry and energy to create a brain capable of measuring these impossible timescales and asking these profound questions. That is the wonder we should hold on to, while the stars are still shining brightly enough to guide our curiosity.
That brief ability to comprehend 10 to the 10 to the 10 to the 56 years, even if our civilization only occupies a single cosmic second, is perhaps the greatest achievement of this entire era.
Something to mull over. Thank you for joining us for this deep dive. We'll see you next time.